Let's get started on Chapter 7, Network Hardware in Depth. In this chapter, we will look at what is a hub, what's a switch, what's a router, and what is the routing information protocol. We will look at wireless networking, wireless security. We will look at types of network interface cards and network interface card installation. So let's start by discussing the difference between a hub and a switch. In the previous chapter, all we said was that a switch provides more bandwidth and that a hub is slower. So let's look a little more closely at the two. To understand the difference between a hub and a switch, it's important to understand what a collision is. So let's review what a collision is. A collision is where two computers put a signal on the same wire at the same time, and the listening computer hears both signals at the same time, and they don't make any sense at all to the listener. So let's look at collisions in a bus topology and a star topology. It's easiest to see a collision in a bus topology. If workstation 1 puts a signal on the wire, that signal is going to go all the way down the wire. If workstation 1 puts a packet on the wire and the packet header says it's going to server 1, and the packet contains ABC, when workstation 1 puts a signal on the wire, the signal will hit server 2, but the server 2 will see that the packet was destined to server 1, so server 2 will just not accept the packet in memory. And when the packet hits server 1 will accept the packet into memory. Similarly, when workstation 2 sends a packet to server 2, the packet will hit server 1, but server 1 will read the header and see it's not for server 1, so server 1 will just ignore it. And when the packet hits server 2 will read the packet header, see that it is for server 2, and will accept the XYZ into memory. So that's if we don't have collisions. The point is, when a workstation puts a signal on the wire, it goes all the way down the wire, and it hits other computers which are on the wire. And that's most evident. You can see it most clearly in a bus topology. So the question is, would it be possible for workstation 1 to send data to server 1 at the exact same time workstation 2 were sending data to server 2? If they were to put data on the wire at the exact same time, what the servers would hear would be a collision. They would hear both signals at the same time, and they would hear this mess right here, SSEERRVV12, AXBYCZ, and that's just the two packets all jumbled up, and it doesn't make any sense to anybody. That is what a collision is. And you can see a collision most clearly in a bus topology. Now let's look at a collision on a star topology. It might not be so obvious in a star topology. So the question is, can workstation 1 send data to server 1 at the exact same time? Workstation 2 sends data to server 2, assuming they're all connected to the same hub. Well, if we see that a hub has what is called a logical bus, a physical star if you look at it from a distance, but you can see it's a logical bus. If you look up close and remove the lid to the switch, you can see that all of these nodes are on the same bus line. So if any one workstation puts a signal on the wire, the signal goes to all of the other computers. And this is what a hub is. All the computers are all connected to each other all the time. That's what a hub is. Now let's look at a switch. With a switch, initially, nobody is connected to anybody. But when workstation 1 sends a signal destined to server 1, the switch makes a point-to-point connection between workstation 1 and server 1, and the packets never hit server 2. When workstation 2 sends data to server 2, the switch makes a point-to-point connection between workstation 2 and server 2, and the packets never hit server 1 as they would in a hub. So now you can see in this example, twice as much data can be sent through this network at the same time because we have two computers which can send data through the same switch at the same time without colliding into each other. So that's the big difference between a switch and a hub. Hub is a logical bus and you get less bandwidth. Switch has point-to-point connections between the ports and the switch and gives greater bandwidth. Now let's look at switches in just a little greater detail. Let's look at what's meant by a switching table. What do you mean by frame forwarding methods? What is the spanning tree protocol? And what is a VLAN, Virtual Local Area Network? We'll start out with a switching table. When a data frame hits a switch, how does the switch know which port to forward the data frame to? And the answer is, the switch has an internal switching table which is in the RAM of the switch. And the switching table shows which port on the switch corresponds to which computer based upon the MAC address. When you power the switch on, initially the switching table is empty. It is built as the switch receives data frames from the network. So you don't need to do anything about it. You don't need to configure it, but it's an important thing to understand when troubleshooting later on down the road. Switching table. Then we have these two frame forwarding methods. Cut through and store and forward. When a data frame hits the switch with cut through switching, as soon as that data frame hits the switch, zip, the switch pushes it right through, doesn't do any error checking. Store and forward. The switch stores the entire contents of the data frame in buffers before forwarding it and performs error checking on each frame that goes through. So this one's faster, this one's safer. Which one's more appropriate, which situation? Well, if this were for delivering streaming video, you'd want the fastest thing you get, and if you miss a frame or two, nobody's going to notice. But if it's banking, well, if we miss a decimal point, somebody will notice. So the store and forward, not as fast, but performs error checking. This is a variable we can configure on a switch. And then we have the spanning tree protocol. You might have multiple switches on the network for purposes of fault tolerance. One switch goes, that's okay, you got the other one. So if there are multiple switches for fault tolerance, how is a frame prevented from endlessly looping around and around, being forwarded from one switch to the other? And that's the purpose of the spanning tree protocol. Spanning tree protocol is a piece of software built into the switch that prevents frame from endlessly looping. It's enabled by default. You don't have to configure it. Now let's discuss page 296, VLAN, Virtual Local Area Network. And here's the situation. We have a single segment network. We got the workstations there, we got the server right here, and we're connected into one single network. And we want to divide the network into two separate networks. We want to separate this group of computers from this group of computers. We'll buy a separate switch. So we buy a separate switch and we create separate segments to separate the computers. These computers on this segment and these computers on this segment. These computers are on this switch, these computers on this switch, both switches feed into the router. The reason that we create separate segments to separate the computers is to 1, limit broadcast traffic, 2, to reduce broadcast traffic, and 3, for security. we take a single physical switch and we create a VLAN. And what a VLAN does is it logically divides the network into logical separate segments as if they were on two physical segments, but they're not. They're on one segment. The VLAN is used to logically divide a network into logical segments for the purposes of limiting broadcasts, reducing traffic congestion, and security. Let's move on to page 30, page 300, routers. The purpose of a switch is to connect PCs to PCs to form a network. The purpose of a router is to connect networks to networks to form an inter-network. And this is a diagram of CCBC Catonsville. And in one building, we have a switch which connects all the PCs together to create a single network in that building. In another building, we have a switch which connects all the PCs to form a single network in that building. In the data center, we have a switch which connects all the servers together. In the middle of campus, we have the router. The purpose of the routers is to connect all the networks to each other and to connect everyone to the internet. Cisco is the big manufacturer of routers. In fact, you can get an entire associate's degree in Cisco routing here at CCBC. We have two networks we want to connect. So what we do is we get a router. And a router is really just a microcomputer with two network interface cards in it. One network interface card goes to one network, other network interface card goes to the other network. That is called LAN to LAN routing. When we connect to the internet, that is called LAN to WAN routing. I can add another local area network, and we can see the purpose of a router is to connect local area networks to local area networks and connect local area networks to wide area networks. This is a diagram of a router connecting three bus topologies, but it could just as easily connect three different star topologies. Here's a router as well, and they diagram the router as a cylinder. The router is diagrammed as a cylinder. And you see that the router connects, in this example, is connecting star networks together. So the router could connect bus networks, it could connect star networks. That's not the point. The purpose of a router is to connect local area networks to local area networks and everybody to the internet. A router is a microcomputer with two network interface cards in it. The purpose of a router, you could say, is to connect networks, or you could say the purpose of a router is to separate networks. If workstation 1.0.0.2 were to send a packet to workstation 2.0.0.4, then when the packet hit the router would push the packet through. In that respect, the router is used to connect networks. However, if workstation 1.0.0.2 were to send data to the workstation right next to it, 1.0.0.3, the packet would hit the router, but the router would not forward the packet through. And thus, any traffic between the network on the network on the left would not interfere with any traffic on the network on the right, because we have the router to separate the network. So you could say the purpose of a router is to connect networks, but it's also used to separate networks. A router either forwards a packet or doesn't forward a packet, and not forwarding a packet is called dropping the packet. A router reads the packet header and then forwards the packet to the network, which has the same network ID as the packet header. If this user was going to send a packet to server 2.0.0.2, when the packet hits the router, the router is not going to forward the packet down to network 3. That wouldn't make any sense. What the router is going to do is it's going to read the network ID on the packet header, and it'll see that the packet is destined to server 2.0.0.2, so the router will forward the packet to network 2.0.0.0. A router reads the packet header and forwards packets. How does the packet know, or how does the router know which network interface card it should push the packet out of to get to the right network? And that's the purpose of a routing table. A routing table is in the RAM of a router, and it shows which network interface card will take you to which network. So when the router receives a packet, it reads the packet header, the destination network in the packet header. It looks for a matching network in the routing table and then forwards the packet out the network interface card that corresponds to the matching network ID. Packet hits the router, router forwards the packet. Now, what if you have multiple paths? What if the user were going to send a packet to server 3.0.0.2? The packet would be forwarded straight down directly to network 3. Now, the packet could have been forwarded the long way around. So you can see there are two ways that this packet can get to network 3, the short path and the long path. The purpose of the router is, if there are multiple paths, to find the best path. And the best path is based upon hops. So if there are more ways than one to get to a destination network, for example, we can see that Ethernet card 2 will take us to network 3, and Ethernet card 3 will take us to network card 3. So if there are two ways to go, which one is the router going to choose? The router is going to choose the path which has the least hops. So a routing table shows the best path to a destination network. Routing table shows the best path to a destination network. The routing table shows which network interface cards connect to which network, and if there are multiple paths, it shows the best path. The manual updating of routing tables means you walk up to each router and you configure it, and you tell the router which network interface card takes you to which network. So here's an example of updating the router. This is a Microsoft router here. So this is the router prompt. So this is the root add command. If I type root add 10.25.0.0 mask 255.255.0.0 space 10.24.0.1, what I am telling this router is the way you get to network 10.25, given a subnet mask of 255.255.0.0, is the packet is pushed out that network interface card, the one that the network interface CAD 10.24.0.1. The root add command tells the router to get to this network, the packet is pushed out of this network interface card. And then to view the routing table, I type root print. That just displays the routing table. And then I can look at the contents of the routing table on each individual router. The manual updating and configuration of routing tables is called static routing. And if you have a large number of routers, it can be awfully labor intensive. So instead of manually updating routing tables, we can use a routing protocol, and this is called RIP, the Routing Information Protocol. The Routing Information Protocol is installed on every router, and the Routing Information Protocol automatically updates routing tables. It broadcasts to other routers every 30 seconds, and it allows the routers to update each other and to find the best path based upon hops. The routing information table broadcasts to other routers every 30 seconds and finds the best path. To install the routing information protocol, and this is something that we would do in the Windows Server class, we would go to our Windows Server, assuming that the router was installed on the server, and go to the IP4 protocol, right-click on General, and select New Routing Protocol. All you got to do is click on RIP, the Routing Information Protocol, and you click on OK, and that's all you got to do to install the Routing Information Protocol. Routing Information Protocol automatically updates routing tables, allows the router to use the best path based upon hops. So, routing summary. The function of a router is to read a packet header and to either forward the packet or drop the packet. When the router reads the packet header, it looks for the destination network ID. Then the router looks at the routing table. And the routing table shows which network interface card goes to which network, and that's how the router decides which network interface card to push the packet out of. A routing table can be updated manually, and they call this static routing, or we can configure dynamic routing by using RIP, the Routing Information Protocol. And if you really like routing, we have an entire associate's degree here at CCBC on Cisco routing. Otherwise, this is the end of part